In 2021, attackers shut down 45% of the U.S. East Coast fuel supply. They never touched a single PLC. They encrypted the billing servers, and the pipeline operators shut everything down themselves. In 2017, hackers tried to cause an explosion at a Saudi petrochemical plant by disabling the safety shutdown system. They were caught only because a controller faulted by accident. This is not IT security. This is process safety. And if you work with PLCs, DCS, transmitters, or control valves, this affects you directly. In this video, what OT cybersecurity is, why your plant is vulnerable right now, and what the real threats look like. Let us start from the beginning. OT stands for Operational Technology. It is any system that monitors or controls a physical process. Your RTD, your pressure transmitter, your DCS, your PLC, your control valve, all of that is OT. ICS stands for Industrial Control System. It is a broader term that includes SCADA systems, DCS, PLCs, and the networks that connect them. IT stands for Information Technology, the systems that handle data, email, ERP, accounting, business applications. For most of industrial history, OT and IT were completely separate. They ran on different networks, different protocols, different hardware. That separation is gone now. And that is the entire problem. To understand why OT security is different from IT security, you need to understand 5 fundamental differences. First, priority. In IT, confidentiality comes first, protect the data. In OT, availability comes first, keep the plant running. Production loss is measured in hundreds of thousands of dollars per hour. Second, patching. IT systems get patched every week. OT systems cannot. Patching a DCS controller means a planned shutdown. At Parco, some of our I/O cards have not been patched since 2009, not because of negligence, but because patching means a 12-hour unit outage. Third, lifespan. An IT server lasts 3 to 5 years. A PLC or DCS runs for 20 to 30 years. It was designed before modern cybersecurity existed. Fourth, failure consequence. A compromised IT system loses data. A compromised OT system can cause overpressure, fire, toxic release, or injury. The physics do not care about your incident response plan. Fifth, protocols. IT uses encrypted TCP/IP. OT uses Modbus, HART, and OPC, protocols designed in the 1970s and 80s with no authentication and no encryption. Every industrial site follows the same architecture model, called the Purdue model. Think of it as 5 floors of a building. Level 0 at the bottom, field devices. Your sensors, transmitters, actuators, valves. Level 1, the controllers. PLCs, DCS, RTUs. They read the sensors and command the actuators. Level 2, the supervisory layer. SCADA systems, HMI screens, where operators watch and control the process. Level 3, the data layer. The historian, the engineering workstation, the jump server. Level 4 at the top, enterprise IT. ERP, email, business systems, and ultimately the internet. Each layer should only talk to the layer directly above or below it. Each boundary between layers is a security zone. When those boundaries disappear, when IT can talk directly to OT, the Purdue model breaks down and every device in the plant becomes a potential target. For decades, OT was protected by a simple fact. It was physically isolated from the internet. No network connection, no attack surface. This was called the air gap. 3 things destroyed it. First, vendor remote access. Your DCS vendor needs to connect for commissioning, diagnostics, and updates. Yakagawa, Emerson, Siemens, they all have remote access paths into customer systems. That VPN connection from the vendor's office is a direct line from the internet to your control system. Second, business integration. Management wants production data in real time on their ERP dashboards. That requires a network path from OT to IT. Every path goes both ways unless it is engineered not to. Third, removable media. Contractors bring USB drives. Technicians copy configuration files. Stuxnet, the most sophisticated cyber attack ever documented, crossed 5 separate air gaps carried by USB drives passed between people. Here is the technical reason OT systems are difficult to defend. The protocols they run on were designed for reliability, not security. Modbus was invented in 1979. It has no authentication. Any device on the network can send a function code 06, write single register, and the PLC will execute it immediately without asking who sent it. Ethernet/IP, OPCDA, DMP3 all have the same problem. They were built when the only devices on the network were other PLCs and engineering workstations. An attacker who reaches your OT network does not need credentials. They just need to know the register address. And that information is in every device manual, freely available online. The protocol itself is the vulnerability. Quick check before we continue. Colonial Pipeline was shut down in 2021 by a cyber attack. Which system was actually compromised by the attackers? Was it A. The SCADA system controlling pipeline pressure? B. The PLC firmware in field pump stations? C. The IT billing and invoicing servers? Or D. The industrial firewall protecting the OT network? Pause the video and think about it. Three incidents define modern OT cybersecurity. First, Stuxnet, 2010. The world's first known cyberweapon targeting industrial equipment. It infected Siemens S7 PLCs at Iran's Natanz nuclear facility and changed centrifuge speeds while sending false normal readings to operators. 1,000 centrifuges were destroyed. The operators had no idea. Second, Triton and Trisis, 2017. Attackers targeted the safety instrumented system at a petrochemical plant in Saudi Arabia. Their goal was to disable the emergency shutdown, not to steal data, but to allow a physical explosion. They were caught only when a controller faulted unexpectedly. If it had not faulted, there would have been casualties. Third, Colonial Pipeline, 2021. Ransomware hit the IT billing servers. The OT pipeline itself was never breached. Operators shut it down as a precaution. The result, 6 days offline, fuel shortages across the U.S. East Coast, for dollars per gallon at the pump. The lesson, you do not need to attack OT directly to destroy an OT operation. This is the fundamental difference between IT and OT security. When an IT system is compromised, the consequence is data, financial loss, reputational damage, regulatory fines. Real costs, but recoverable. When an OT system is compromised, the consequence is physics. A control valve commanded to full open. A pump running above its design speed. A heat exchanger above its design temperature. A safety instrumented system that has been silenced. Physics does not have a rollback function. At a crude oil refinery, a 40-degree increase in heater outlet temperature does not trigger an automatic safe shutdown in every scenario. It requires an operator who is watching the right screen at the right moment and responds in time. That is the consequence gap. That is why OT cybersecurity is not just an IT department problem. Defending an OT network does not require a cybersecurity degree. It requires 4 disciplines applied consistently. First, segmentation. Separate your OT network from your IT network with a firewall. Do not let them share a switch. Do not let IT systems talk directly to PLCs. Second, inventory. Know every device on your OT network, its firmware version, its open ports, its vendor. You cannot defend what you cannot see. Third, Access control. Vendor VPNs should only be active during scheduled maintenance windows. No standing remote access. Every session should be logged and reviewed. Fourth, monitoring. Deploy passive network monitoring on your OT network. Tools like Clarity, Dragos, or open-source solutions like Zeek can see every Modbus read and write without interfering with production. When something unexpected happens, you need a record. These 4 pillars will not stop a nation-state, but they will stop the vast majority of attacks that target OT systems today. You have spent years learning how these systems work. The physics of pressure and temperature. The loop from sensor to controller to actuator. That knowledge is not separate from cybersecurity. It is the foundation of it. An IT security team can learn firewalls and protocols in weeks. They cannot learn in years what you already know about how a refinery actually behaves when something goes wrong. OT cybersecurity needs people who have walked the plant floor. The next videos in this series cover network segmentation, the DMZ architecture, and how attackers move through an ICS network step by step. Subscribe so you do not miss them.